So today I'll talk about three era, let's say. First era is actually, Power is very familiar with the FSE and the 22 works in Singapore and the one TSE work, and the industry calls probabilistic testings. And then after this TSE, FSE, I present our work as open source tools towards the BYD headquarters in Shenzhen, and the NEO Nasdaq listed right now headquarters in Shanghai, and the Baidu Apollo headquarters in Beijing, and they give a lot of challenges and new opportunities. And based on this one, we are actually working on this one, which is the present work. Is actually a move from probabilistic testing towards formal testing to revive something called model-based testings. It's FS'24 vision paper. Based on this one, we create two technical papers. One's ICSE’25 in Canada, we presented, and then the TSE’25 paper implement this vision. Last, I'll talk about future work is make the AI system from black box and stochastic nature towards something you can verifiable, open this white box, or people call gray box, called neurosymbolic. 27, we actually start the work, very similar time, like many researchers, I think Paul was doing this. Industry people complain so many safety issues. On the left-hand side, Tesla car crashed into different kinds of white objects. And recently, they also crashed into Taiwan, a turnover car. But people blame because they're using only camera. On the right-hand side is Xiaopeng P7, is one of the three startup companies, very quickly rising companies in China. They not only using camera, but also millimeter radar and ultrasonic radar. They still crash into turnover stationary objects. So the safety issues very deep down into the system itself, not only the sensor modalities. And in FS'22, I remember Pyro hosting the session. That's the first talk in the first session. We present this work, and we spent 3 years to bring down the brick wall by the autonomous companies. We interviewed 10 companies from Asia, Europe, and North America to get their practice, how they testing systems. And then based on the finding, we do a quantitative survey about 100 industry practitioners. They give the review, and then we have the practice needs and the gaps. This is open in the archive. And I will highlight some key findings. The first key findings, I think I will move this one around. This is very confusing. Yeah, I can't do it. See? It's disappeared. There's anything we can do it? Yeah. Maybe here. Oh, no, I can't.
Out of the presentation mode, and that mean again.
Yeah, I'll do it again. Okay. Oh, God. I don't know. I'm sorry for this. Hopefully it won't block too many. So I just highlight some key findings. On the top right is actually when we started the work, computer vision have a lot of people working on end-to-end AD systems. So they have neural networks take the sensor input and output actuation commands. And we found the majority corporates we interview and survey, they use these multi-module systems based on ROS, robotic operating systems. And the Baidu Apollo have their own version called CyberRT. And they already achieved the synchronization latency towards milliseconds level. And Tesla rejected the interview, of course, for all sorts of reasons. But they said Tesla is 10 times faster, right? So the synchronization among multi-queue this kind of distributed system has been solved by industrial peoples. And you can see a lot of modules inside. You have a lot of different machine learning models, you have different modules. So it's machine learning model, lots of them, and also a lot of rule-based modules like controllers behind the system. So system is very complex. In terms of emerging needs, they have the corner case identification. Baidu Apollo quality control manager Li Haizhou told me the corner case is not really the crash case, it's actually all these cases they haven't captured in the real world. They want to see how their vehicle system behave in such kind of systems, in such environment. Speed AD is testing because they have very quick CI/CD pipeline. They have to deploy the product. They have very limited time to run all test cases. You have to do test reduction and test ranking. And the third one is actually in China, robotaxi has to go to physical testing centers, right? So each time go to a physical test center is impossible. So they have to create the roughly similar scenario in the simulation. To recreate this scenario is very difficult. The last one is to support for data labeling, because all sensor data is unlabeled. To label this data has a lot of human errors. Human is not good to give this kind of data labeling correlates, and they face a lot of problems with this rubbish in, rubbish out problem in the machine learning model trainings. So this is FS'22 paper, another paper we presented. So this is the test reduction, and you can see this Australian government has this project. You can simplify it as a rear-facing camera. Okay, when the vehicle is driving on the Australian highway, they want to reduce from hundreds of hours to like a few minutes driving recording in the simulation. A simple naive is to just buy the scenario classification, right? Highway, townway, but you cannot do such thing in Australian highway because in Australia we have a well-known animal called kangaroo. In Australian, kangaroo is not only one kind. We have at least more than 20 kinds, from little mouse to all towards 180 centimeters high red kangaroo, very, very muscular, all muscles. They are very aggressive. So your car approaching their territory, they will attack you. Not only attack you, but also attack your car. How to attack? Kicking. Use very strong legs to kick your cars. So if I have car close to the kangaroo, you don't know what would happen. Second thing, we have another animal in Australian highways called wombat. Wombat is my favorite animal, not like koala, but wombat has a very strange behavior. When the vehicle approaching him, it select to not run away. It choose to turn his back towards you. And then your vehicle system from sensor fusion will look as like a lock. We tested, it look like a lock in the dark weather. Then your vehicle has two options. One is changing steering angle, second is breakdown. But in Australian highway, we don't have the Eurostar like here. We don't have train system. All the logistics done by very heavy trucks, right? Also, a lot of highways built on top of the mountains, and we have a lot of rains. So if you change the steering angle, you slow down very quickly. It's very dangerous. Off the street, not off the street, off the mountain, or collide with the incoming trucks. So it's very dangerous. So what we suggest is actually frame-to-vector. Because industry already resolved the problem of synchronization to milliseconds, right? Which means in any critical time t, you can construct a big frame from all the message queues, which contains the sensor input and the module output. The module output contains the oracle data, which we can use for regression testing, right? Okay, then we contain this driving recording. We name this as a frame-to-vector. The reason to vectorization, because vector give you a very good property. You can calculate vector distance using LP norm. You also can calculate the angular distance, use dot product, right? Now you can, if the difference is very small, you can think they are same. You can color coding them. If color coding the sequential frames, then you can compress them. If you detect the frame again, you can think it's a duplicate scenario, you can remove them. You can do the compression and the removing. That's exactly what we do. In the end, you have all the unique driver recordings, which has the heading and the footer, which allow you to learn independently, okay, which have some context information inside. But the industry say, James, even all the unique test cases I cannot run, I don't have enough test budget, right? And I remember present this when UPenn or like tell me, James, I want to believe you, but I don't trust this is true. How can a business owner determine the time to release the product? I think this is a reality, right? In autonomous vehicle companies, the time to release is not determined by technician, it's determined by the board of directors. And then you only have limited time to run all test cases. What can you do is actually rank them. Select the most important unique test case to run, right? What we do is actually, because vector has different scalar, we're actually using one hot encoding. One specific one means like a kangaroo passing the street. Another one means the red light. Another one means the jaywalking pedestrian, right? The vector has the most of one, which means have most of the semantic coverage. You rank first. Now, even that, you don't have enough test cases. You don't have enough budget to run all test cases. You need to break time. What we do is look at all the chosen higher rank unique test cases to check what kind of semantic information happened least. For example, jaywalking pedestrian only happened once. That one has to be moved first. It's diversity, right? We have the coverage and diversity. The results are very good. So the industry partners select 4 modules, which is very critical modules, have 3 maps in the Baidu Apollo systems. We have the minimum 34% test reduction, maximum 77% test reduction. But people say, oh, you removed so many test cases. Did you miss any critical bugs, right? So we do the mutation testing. Each mutant is selected from the Baidu Apollo repository. It's a real box. We reproduce it. And then we want to see the mutation kilo ratio. You can see 100% almost. The only thing fluctuates is 92% because sharing the traffic light, the original oracle, when we capture the data, is not stable. The system is not stable even without regression testings. This is open source, okay, one open source tool. Second open source tool we collected is actually they have a lot of real world data collected, but they can't test it with the pedestrian edit, slow sign edit, remove lane line. What we do is actually then ask them to write if-then statement. If is to describe what kind of scenario you want to generate it. It's like data augmentation, right? and then describe what kind of relation you to check. This obviously is metamorphic testing because you don't have oracle, right? We know you have original driving scenario, you have the speed, you add the pedestrian. We don't know the oracle speed, but at least compare the speed should slow down. That's a metamorphic testing. Similarly, remove lane. If we remove the lane, the steering angle should not change that much because humans still can construct artificial lane. Can AI does that, right? This is similar things. So when people click generate test, multiple things happen. For all the A2, D2, or D data set, for every single eligible images, we do a transformation. We apply machine learning model to the original one and after one to check the results and to compare the results whether the relation is violated. If violated, we report it. If not violated, we show it. And then we also want to show how fast you generate all these kind of testing cases and give the results. So this is all the results in the TSE paper. We have 3 models, test randomly select 7 rules. We have different violation ratio. For the most complex rule, they select rule 4. Entire RD data set is 5 minutes. And you can see how many optimization we've done. That's software engineering hard work. And we also evaluate the authenticity. Actually, it's not authentic, it's a consistency between the follow-up test case and the original test case. They have to be consistent. This Amazon took, you can see 7 is identical, 6 is similar. You can most 6, which means we actually generate proper, consistent follow-up test case compared to original test cases. Open source as well. All right. With the TSE and the support from Palio and the other people, I'm very proud. So I just present my work to the industry, see what the feedback. So I present the work at NEO in Shanghai, Apollo in Beijing, and also BYD in Shenzhen. This is fulfill the Australian Research Council projects. We have papers, we have open source projects. They point this one, James. Frame to vector is hundreds of dimensions. This is good for Australian environment, but what they're facing is very complex. These Chinese companies, they deploy a car into a city called Chongqing. Has anyone been to Chongqing before? Chongqing is a hill city. Everything is built on top of mountains. People call it AD dimension. Yes, a lot of people ask, James, I only know XYZ. What do you mean AD? In the final talk, I'll give you the pictures, understanding what the other 5 dimensions come from. It's really hard. Then you cannot do this schema. You have to learn it. But the problem is, if you learn this one from latent vector, right? Which means latent vector has to be accurate. That's chicken egg problems, right? The second opportunity they point out is, James, you do the crash report, you do the traffic rules, but they have a lot more richer information. They actually install front-facing cameras. I know this sounds like ridiculous because how you can collect all this data from all the vehicles, but it turns out they have terms and conditions already signed by the people who buy the car. So the front-facing camera capture all kinds of data happen in the real world. If you have a car crash, few hours later, from different vehicles, you can actually, the car company can collect the data to show from the beginning to the end how the car crash happens from different angle even, which means if you can access to this data, you have very good foundation model, you actually can do the corner case generation, right? They solve these problems. This corner case generation is very good property. Later I'll talk about why it's very good property. This is the limitation. This is the opportunity. I talk about challenges. These are very, very big challenges. It turns out for this autonomous company, Scale AI in United States, and also there's another company called, I can't remember the name, sorry about this. They do the data labeling for Apollo. They actually need to do this bounding box. The human has to put a bounding box around each object. The bounding box and put the object label to it. The bounding box has to be tightened to the pixel level. I think you can imagine how hard for the human to give the required quality label for the industry, right? The second thing, actually, this is images. What if you have multiple images, right? How you can label it? More importantly, point cloud. Point cloud data is not 3D, it's 4D because you have 3D point cloud plus time dimension. For the point cloud, it's even harder for the human to give these human oracles. Human cannot do it because this problem, we have a lot of bad label data into the training pipelines, causing some kind of near collision problem for the vehicle systems, especially in Chongqing, these kind of complexities. It's very, very big challenges. I will talk about this one in the future. But this problem, not only ADS, but also Zheng systems. We have Zheng company in Australia. They want to do this markerless landing. They want to remove the marker as safe guardrail and just give a GPS coordinates or map coordinates and ask the drone to land. This is dangerous because if a drone lands into a slippery, uneven places, it's crash landing. It's not normal drone, it's a big drone. They actually deliver the blood example to the hospital organ to the hospital or the equipment to the farms. We have a lot of farms, like Switzerland, we have a lot of farms. We deliver these automated repair stuffs. It's big drone. It's crash landing. Or even land, the land is soft because after rain, it's too soft. The drone cannot take off. You have all sorts of problems. And we have a lot of billionaires living in Australia. They have yachts. They want you to deliver the best French champagne, Italian wines or something, or even coffee. And then the billionaires walking around the yacht, they have a lot of people walking around the yacht. The billionaire won't give you the marker. Just tell me, follow my yacht and deliver. It's hard. And because of the ugly Ukraine war, the people approach the drone company with the requirement to do helicopter landing. The helicopter has to land in a hostile environment where you don't have the maps and the GPS denied, of course, right? Signal war. They have the GPS denied. It's getting harder. Why it's hard? Thomas Zimmerman in 20, here I have the data, 2019 has put a position paper, talk about why it's hard, because in this kind of learning-enabled CPS and in any machine learning-enabled critical systems, you have these two pipelines, data and machine learning models. Data is very difficult because you don't even have province guidance for the data. You don't even know the training data come from. Right? This is really difficult. Second thing, for the model, you don't really have proper verification methodologies for machine learning. All the testing I know is black box treating machine models. Right? It's a stochastic nature and softmax distribution. So we set up this working group. We used to talk about working group more like a workshop. It's more like a working group. The first working group in San Diego, 2024, they told me this is actually ICSE’22 come from. An international cyberspace system coming from. So we have all the people I can think of united together. We put this 24 vision paper I introduced in Brazil. So the idea is simple. We want to revive something called model-based testing, or people call conformance testings. The reason the model-based testing and the conformance testing died down is because specification is missing. So industry will not use it. None of the industry we know they use this conformance testing from ADS industry. And the researchers actually also died down kind of in this kind of area. Australia, we have people doing it, but it's not very popular right now. So we want to revive it. To revive it, first, we have to revive the specification. How we get specification? And we look at the different kind of data-driven learning called active learning. L-star learning is from Yale, 1987, called uncrewed learning. So it's basically from the data, you do some membership query against Oracle to check whether this underlying specification. But this L-star learning also died down because you don't have enough data. You see the problem? And this is actually all the way back to the data. So this is the data. I said before, you have a lot of rich data from the CPS. Zheng has the surveillance data, ADS has front-facing cameras, and you can use this rich multimodal data, use LLM to generate all kinds of corner cases. More corner cases generated, it's easier for L-star learning to learn the specification. Right? Once you have the specification, it's easy to revive the model-based testings. This tool has not been resolved yet, especially model-based testing. I have some idea. Maybe later we can develop a code develop with Parallel about revive these model-based testings. We have some idea, but I will talk about two things. First of all, we have a technical paper to prove how to use LLM to generate corner cases from the input data. Second thing, in L-star learning, active learning, it's very important to have very good simulator. Because simulator data is generating simulator, we learn from data, right? So simulator has to be real. So this simulator fidelity gap is another paper we produced. So I focus on these two papers. First of all, LLM. How to use LLM to generate this diverse data, right? Okay, this is the TSE paper, just get accepted. So I know people of software engineering has so many people use LLM to generate test scripts, right? We argue it's very hard to use LLM to generate test scripts for ADS systems and for machine learning enabled cyber systems because the brick wall put by the industry. Those very good, lots of line of code of test scripts, we cannot get access. No one open source it, right? Which means the training data set for LLM does not have this training data set. Because you don't have training data set, we all know it's covariance shift. The LLM will hallucinate, right? Okay, to resolve this one, we actually designed a DSL. In ADS, we know there's an industry called open scenario, right? But using open scenario to describe a scenario is very complex. Then changing is 250 lines. There's another one that's very, very detailed called Cynic from UC Berkeley. But Cynic program requires to you as a developer or tester to specify the row condition parameters. It's so hard condition to specify this one using LLM because it will hallucinate again. So we designed DSL, it sit in the middle, semantically rich, syntax easy, and also compositional. Why we have conversational? 2 reasons. First of all, conversational allow you to create specific validation scripts to check whether the output from the LLM for that specific environment, low network, hallucinate or not, right? You have specific validation. Second thing, from NIPS community, they believe for LLM, if the input token, which is prompt, is too big, the LLM will do something called compression, token compression. More they do token compression, easily the LLM will lead to the hallucinations. So the input should be smaller. Because you have a compositional, your input will be smaller by nature. So it's a divide conquer, both from input and output validations. Works, right? So this, which means for every single traffic rule, we can design, we can derive a quite faithful representation in DSL format. But people thought, hey, scripts, what are scripts? You just learn the representation in DSL, right? How we does it is actually we do the program synthesis. And the PR community people say, James, you have to do tricks. Yes, we do tricks. How do we do tricks? Because we know all the simulator. For all the popular ADS simulator, we create template. Everything inside, right? Everything is intact, except the parameter for that specific scenario. The parameter is missing. From the scenario, from the knowledge representation for the traffic rule, we do a search to find suitable scenario parameters, and back to the template, you done the script generation. So it's a trick we did. So this is all we done. So the open scenario is very complex as before, then changing 250 lines. Cynic is actually required to specify very, very detailed parameters. It's very easy for LLM to hallucinate. They try using Sanchez settings. They have generate syntactic correct, semantically wrong scripts, right? So that's a big problem they're facing. This is the scenario. This is the script we want to generate it. So we create a template for it. We actually try a pilot study. We generate Cynic and the color scripts directly. Doesn't work because you have all these problems. This is the DSL design. You can see it's compositional design environment, design neural networks, actor, ego, and the MPC vector, which is other dynamic objects. We define the oracle, and this is the knowledge extraction pipeline. So we have the DSL design. We showed the context learning, and then LLM generated the knowledge representation. We do the validation twice. One is a knowledge validation, a syntactic validation, another semantic validations. And then this is template we generated for each simulator. And how we do search? Okay, first of all, when you from rule, you go to DSL representations. First of all, it's from all the maps to find the suitable maps, which is corresponding to your description. And from the the sub-network, which is exactly described by the low network, right? So the first part that we call hierarchical search. Second thing, from all description, find where is the first suitable position from the ego vehicle and endpoint vehicle. You have the waypoint set up. Then because you have ego vehicle, you can set up the other dynamic object vehicles waypoints. Then you have all the data. You just extract this data from simulator, put back to your scripts. It generates the scripts. Okay, that's all we done. So a lot of nice tricks we did. So in terms of the research question, first of all, to check, compared to the human written DSL representation, how accurate is your LLM learning, right? That's one thing. Do you have a lot hallucination? Second thing, you generate the scenario. How consistent the generate scenario with the original input, which is the test rules. The last one is utility. Oh, okay, can you detect some issues, right, for the AD assistance? We test S3 simulator, which is popular simulator. We test 6 model industrial popular ADS. The 8 AutoWare and Apollo 7.0 is multi-module system I talk about, industrial grade. Apollo 7.0 is the same foundation they run the robotaxi in China. Of course, they have different version for industrial, but it's the same foundation. They have the different ARM using to check the URM performance. So you can see the first column, the second column is actually our results for our solution and all this ablation study and the different baselines. You can see with all this verification and the validation and the compositional input, we almost achieve 100% accuracy compared with a human written oracle, right? Which is good. Second thing is actually generation. We have 90% generated successfully. 7 and 3 is because different simulator have the game engine behind. For example, Kala does not support the ambulance artifact. Of course, it generates failed, right? You don't have this support. And in terms of the scenario consistency towards the input traffic rule, we've done a software engineering students. I'm teach software engineering, so I have 100 students volunteer for for the check, they check, oh, it's all very consistent with the traffic rule. Of course, it's quantitative, it's not qualitative. So we get the prolific workers, and you can see they are mostly consistent, right? Mostly consistent. The only thing that actually fluctuating here is just because of the simulator does not support the lane lines, like a non-broken lane lines, and why the definition is different. The simulation has some issues, especially the game rendering, and the statistic difference is very low, which means which is good. I want to talk about some root violation. I'll talk about specific timeout. Timeout is actually bad word. It's not really timeout. It's actually called motionless. Recently, Xiaomi Su7 has a very bad collision. 3 people died inside the car. It's because the car was facing a scenario where they have low network changes. They have traffic cones to regulate the map, and the scenario is different. So when the vehicle facing a scenario, what he did, the vehicle does is, I don't know what to do. So they revert from autonomous driving to manual driving. But unfortunately, it's late night. The 3 female people in the car sleeping. So when the female driver is waking up, it's 1 second before the collision. 100 kilometers per hour driving speed. So no one can 1 second to avoid this one. So this timeout is very dangerous. Of course, how they switch them automatic to manual is problematic, right? How can you give 2 seconds within 100 kilometers per hour? But the problem is timeout. So the vehicle system is input into a scenario, they don't know what to do. That's very dangerous. So this with Detect 7, we report to Apollo 7.0. They say, James, give me a talk again. So in October, I'll give the talk in Baidu Apollo to show them why they have these failures. They have 9.0 right now, I believe, or 10.0, 9.0. They have new systems. Okay, another one is simulator. I said before, to extract specification, you need the data. The data has to be generated in a high fidelity model, but mostly data is generated by simulation, right? But simulator has a problem called fidelity gap. The one problem of simulation fidelity gap is a lot of online testing, the dynamic object trajectory is predefined. But in the real world, in every single time t, the next waypoint for dynamic object is not predefined. It's dynamic impacted by other vehicles and ego vehicles positions, right? They have dynamic interactions. But to do that in system, they call adaptive stress testings. But to do this, you have to really either do abstraction of this behavior or you do deep reinforced learning. Actually, it's more complex, called multi-agent deep reinforced learning. It's very hard to converge. Either do abstraction, which losing the fidelity, or it's cannot converge at all. We tackle this problem using 2 approaches together. First of all, we all know search-based testing have been around, very good. They have different algorithms. We use the old one called NSGA2. We're not even using the new one. What we want to do is this. The Zheng company wants to deploy the car, the blood bags and the live organs to the hospital. Unlike Google, just drop it. You cannot drop the blood. Or like Chinese companies, they have a very safe infrastructure to land it. In Australia, just give a marker in the car park, hospital car park, and land. And you have ambulance, you have cars, right? It's very easy to collide. So we do the offline first, using the search-based testing, give some fitness values, multi-objective fitness functions to focus the search domain towards the car park. Actually, they can do it because you don't really care about the main road and the people walking on the balcony. They actually can focus, kind of. We actually test it on the car park areas. And then you have this thing, surrogate training. Another thing hard to converge is because the game engine produces very beautiful trajectory, continuous trajectory, like the car moving very good because game, right? But for me, I don't really care about the acoustical effects, right? I just want to know in any critical time step, what's the position of every single dynamic object. So I convert from the continuous trajectory to a sampling of the discrete events. We sample it. Then people, the students say, James, look ugly. It's like a zombie jump. It's like a zombie jump from one point to another point. Just jump. You don't have artistic trajectory anymore. Because what I really care is the points. Once you have these discrete points, you actually can train. It turns out surrogate training only 1 hour. The DRL converged. And the third tricks we did is actually we don't use multi-agent DRL. We use distributed DRL. Once you train in surrogate training model, 1 DRL, you deploy to every single dynamic object in the simulation. They work independently. It still works. Of course, maybe not as good as multi-agent, but it works because in the real world, how they can collaborate? Each one is still working by its own, right? Okay, then this is the multi-objective. We have the genetic algorithm. So we define the chromosome, we define the fitness function, distance to length, time to length, diversity. Nothing new. It's all engineering efforts. And we also have this mutation, crossover. Everything is very standard. The thing I want to talk about is how we do this online reinforced learning. The state we describe is a relative term. Relative towards the position of the marker and dynamic objects, each dynamic object, and position with the UAV with the marker, right? It's all relative term. The reason with relative term, it can generalize to different scenarios, right? We can remove the environment factors. Actually, it's discrete and not continuous anymore. Up, down, left, right, stationary. We predefine the speed for every single dynamic object. Car has the speed. Cow and the dog has different speed, right? We define this speed threshold for them. Reward is a cruising or the collision, and it works. The surrogate model, surrogate environment, I don't want to explain anymore. We have 3 research questions. First of all, different marker-based learning system, what's performance? Second thing, towards the SOTA, what's the performance? The last one, I think it's the reason get accepted ICSE is actually all these problem found in simulation can reproduce in the real world. We actually can. And I showed actually very, very deep down safety issues in machine learning models, in different machine learning models using. It's multi-module system as well. First of all, this is the map we created. As you can see, we do a lot of things. It's Microsoft ASIN. We changed the simulator behind to make support to some different maps. Okay, we have 3 learning systems to test, all given by industrial peoples. They are different systems they are very familiar with. We test 5. Sorry, the last one is called the surrogate train without random mutations. So we're testing 5 different diverse matrix, violation ratio, top 10. Parameter distance 3D is diversity. Time consumption, less time is better. Top 10 is fun. Top 10 bugs, how many test cases needed, less is better. So in all this baseline comparison, we actually perform better, especially in the violation and top 10. But we have 1 hour additional, which is fine. Industrial people say it's justifiable. I show you some arrows, why they justifiable, and they deploy to a production line. The first bug we found is very, very interesting. This is this one. Sorry, I'll ask the students to put the leaf, they put branch. And you can see the leaf and branch have different meanings, right? It should be leaf. If a branch, of course, you should not land, right? If leaf, you can. Okay, the problem is the computer vision guy worked with us, trained something called TPH Euro. It's an advanced version of Euro systems and Euro V5, V7, and allow you to detect small objects very, very far away, like 50 or 100 meters away, which is very good. Everything's working fine. But when we deploy it to JSON nanobot on the UAV, it cannot detect this when you have occlusion. And the computer vision people say, James, something wrong. It's the wrong different models. Then we check the model. It's exactly model he developed. Why it happened? Okay, because he developed is Python code, right? When we deploy Python code to C++, you go through something called CyberRT. Oh, sorry, not CyberRT. Python RT or Python RT or TensorRT. Sorry, TensorRT. So the TensorRT does is actually you compress convert from Python code into C++ code. One thing they did is called quantization. They compress from 32 bits of model parameters into 4 bits to fit into the model to the board. But when we quantization compress the size, what you lose is the generalizabilities, robustness. Something loose, right? Something loose is here. Generalizability. We have different UBCon paper to prove how to do it properly. We call low rank approximation. It's a lot more mathematical sound and rigid than just do a compression from 32-bit to 4-bit, which sounds very random and arbitrary, right? Another thing we did is this. So this is even worse. So they take something from robotics champion, ROS, the local path planning. When you have obstacle, they create local path planning, the waypoints, right? This is fast, efficient, win the championship. And they took it. They think, James, it must be working. But they forgot something. That championship is working in a fixed environment. To fly around some static obstacle, right? Static obstacle, which one get it's like racing, like racing. Who get the targets without collision fast will get the championship. But the problem they facing is this. So when they have the local path planning for every single obstacle detected, they have a buffer, which makes sense because buffer prevents the collision. But something they haven't tested properly is actually if in the buffer you have suddenly a dynamic objects. What happened is for the path planning is crashed. When the path planning crash, there's like a crashing failure. What happened in the Jetson nanobot is actually this controller, Arduino Parrot, and the PX4, they crash as well. The Zheng 4, these are small Zheng, people can hold it, but that's a tens of Zhengs. No one can hold it like a magic power. We hold it, right? Well, crash. When we crashed in the hospital, very, very bad, right? And the industrials sent an acknowledgement letter to us saying, James, fortunately found this problem because they were deployed a few weeks later to the hospital. They found this problem, they remove it. How they remove it, I talk about another paper. How we replace it. Determinist code, not a new network anymore, to do the path planning. Another problem is actually interesting is actually the object, dynamic object detection. So you have a ball passing through, like a very quick ambulance goes through the car park. Somehow it cannot detect anymore. Once again, the computer vision guys very panicked. Damn, something wrong. And then it turns out 3 problems. First of all, probably with the quantization, we cannot show. Second thing is actually frame. When he trained his machine model, he has at least 20 frames per second. But when you deploy it to the drone system, you cannot take 20 frames per second because it's battery hungry. Maximum is 4 or 5 frames per second, maximum. The third one is there's a MAV-ROS link connected to ROS, right? The MAV-ROS link from the board and board have a communication latency. Plus the model has the inference latency, cannot detect it. Frame per second, communication, inference latency, 3 add together, you cannot detect this one. So this we're also doing something about it. Okay, this is all testing, right? To make the model-based testings. Even for model-based testing, it's only 1/3 of it. We haven't finished the model-based testing and the formal specification extraction yet. I want to talk about something very urgent, is actually how to make system itself verifiable. When I finished my PhD and landed a job in Melbourne, I rent a car, like in France, even in Paris, I rent a car. I rent a car and drive in the city because I tired of the Texas beefs. I wanted to try some Chinatown. I drive in the city. In Australia, we drive on the right-hand side. So when we turn right, you turn from the rightmost man, right? And I found I cannot do it because in the middle, we have train. When the green light is on, train is moving forward, you turn right, it will collide, right? So what they do this hook turn. Your car is moving towards the leftmost lane, go forward, there's an island reserved for you. You change the heading of the vehicle towards another direction, waiting for the green light. You're waiting for 2 green lights and to go. At that time, I was panicked. What I do? Imitation. I follow other cars, right? And of course, the machine learning people I visited before, UCLA, Paris, I say, James, this is imitation learning. But the difference with imitation learning is when I copy the behavior of the vehicle, I'm reasoning as well. Why I move to the leftmost? Oh, this is this part. Why in the changing lane? This must be an island. This arrow means I have to wait for a traffic light to turn green. Now, I'm not only follow the cars, I'm also reasoning. This is called system 2. System 1 inference is good by machine learning communities. System 2 reasoning is significantly lacking. They don't have inference. They don't have human level reasoning, even my reasoning at the panic mode, they don't. This is Chongqing, okay? In Chongqing, when the car is driving for half an hour because of the hilly mountains, your vehicle vertically same spot. Your Kalman filter failed because how can half an hour driving, I'm still in the same spot? It's not the right way, right? Second thing, traffic light. For each lane, because you have so many complex roads way out, even more complex than the roundabout of Triumph in Paris. The roundabout of Triumph has 10 roads. They have more complex. So each traffic line has a dedicated traffic light. But which one is yours? Because there's not a line horizontally, it's like this. So the only thing you can do is elimination. What's elimination is to see if the car is moving, which traffic lights turn green. Then you know by reasoning which ones belong to you. If multiple, you do more reasoning, right? And then machine learning does not have these capabilities. And this one's even more dangerous. In Chongqing, because the hilly mountains, it's very, very like curvatures. If you drive from 32 floor in one building to another ground floor, they actually level in the same level. Which means if you want to drive straight, the only way is drive passing the building. There's a road inside the building you drive through. And for autonomous driving, my God, it's collision, right? It's suicide. Only you have a human level reasoning and prior knowledge. You know this is safe. You can do it, right? For the ADS system, especially at night, you can't see the building. You only have the road. You cannot do it for the ADS system, right? But for human, I know because this road I can go. So this human level reasoning. So we have another keynote speaker, that's another meeting, TSE’24, especially Zheng and Armando, they are neurosymbolic pioneers. We have this paper out in 25 in Norway presented. We want to present neurosymbolic. Yeah, as people have different neurosymbolic concepts. The professor at Oxford, 3 professors, each one has each individual interpretation of neurosymbolic. Our neurosymbolic is very different. It's not like a neural rules and symbolic solvers, symbolic solver, neural rules, or private validation. We are actually tightly bounded. So we argue from all the data set, you can use something called neurosymbolic distribution. It's basically train a DRL to learn a policy. You convert policy into automata. Once you have automata, you don't give the developers automata. You hide in a very good syntactic sugar called DSL. You define the DSL for the perception. You define the DSL for planning control. And from DSL, you program synthesis, neurosymbolic map. So what's the neurosymbolic map? So you have a neural components, right? You automatically generate the bridge between neural to the symbolic AI, which is the prologue, for example, or scallop. The variable and the feature they mapped, right? You build the bridge automatically from the specification. And then from the SynGraph program and the global planning, they are symbolic program by itself, have no neural components. How they did it is actually the program induction. When your system is evolving in the real time, they're observing from the underlying semantic map, you can automatically synthesis or induct it, the programs, okay? And all this one is actually not data-driven anymore. It's a specification-driven. You can see very different. And the learning for the neural component is not by data label, it's by the specification. Okay, for this one, you have to resolve 2 problems. First of all, if I have a specification, can the neural component, as I said before, can the symbolic constraint can make the neural to adapt it? First question. Second question, if you have semantic map as a foundation model, can you generate automatically the SynGraph as a pure program, like a first order logic, to determine where to land? Right, these 2 hard questions. First question is resolved by this paper called Laser. Zheng is a graduate from UPenn, now is working in Johns Hopkins universities. The paper is this. So you have a video taken from ego-centric vehicles. You have a natural descriptions of it, right? What he did is actually use the LLM to generate the temporal logic, and use the temporal logic to guide the generation of this spatial temporal SynGraph, the neural networks. How he guide it? Because scallop is a probabilistic languages derived from prolog, actually data log from prolog, scallop from data log. So he can generate, for currently your SynGraph generated, how far away from the temporal logic specification conformance. He calculated a conformance score, and the conformance score as a loss all the way backpropagate from probabilistic symbolic languages to the neural network generated spatial temporal SynGraph, and train towards the SynGraph generated conform to the temporal specifications, which is cool, right? You basically now using the data to train a neural network. Use the specification to train neural network. Of course, the limitation is only one single camera can't be sensor fusion, right? This is another things we can work on. The second thing I want to prove, if you have a foundation model like this semantic map, right? Semantic map, can you generate the decision layer purely in a deterministic program to determine where to land? For example, this market landing. I talk about this helicopter scenario, right? You don't have maps, yeah, you don't have GPS. The only thing you have is the camera, down-facing camera. How you determine where to land? There's no marker. The enemy will not draw a marker for you. You have to detect where to land, right? So this is the hard problems. So what we do is this. So we actually have the semantic everything as a foundation model, which create the clusters of all the scenario, right? I give the labeling. And from that one, with human in the loop and the LLM, we synthesize automatically first order logic. The first order logic to determine where to land, right? For example, on the right hand side, you can't see it, is actually we know this most like river with this dangerous to land, we give the reasoning. And we give reasoning why land here because it's far away from all the possible water landing places. We give a decision. Here is similarly. So method A is use large language model created by the industrial competitors. You can see large language model can hallucinate. The drone cannot land on this white spot, right? And on the method B is actually using by the optical flow and CNN models. You can see it's easy to collide. This is done by the transformer networks. You can see also collide. Our scenario is actually land here. This is not the best, but the safest one in all scenarios. You can do emergency landing. The good thing is about it is the first order logic is automatically synthesized semi-automatically with human in the loop sometimes. And also, we give the labeling. Label is not data labeling. We actually give all the bounding box red and green. Red is unsuitable, green is suitable. We give the first order logic terms, and the human can edit, remove, or add the new first order logic in a DSL format and help to train the neurosymbolic programs. So it's not trained by data anymore, trained by human level reasoning, which is really cool. This is actually we deploy to Sky networks on the stages, do the real-time testings. So we have a continuous integration testing with the simulation. The next step is neurosymbolic. I said before, for industry, it's very hard for them to buy your products because they want technical maturity level to the, if 1 to 9, they want to 6, 7, 8, 9 before they invest and believe in you, like Pyro does the software development. We also do development for the Zheng company. We develop the Zheng landing system for the company, for startup companies. And you can see we divide these multi-module systems. We have a state machine to determine where to land. We replace the path planning from neural network towards like a rapid random tree, which is determinist logics. You can give more probabilities, the assurances, but still we have these problems because we don't. The Zheng is taking an optimal path, but it does not have it has the blind spot here, and also window can open. So this one can only be avoided by symbolic AI. We can have rules change it, right? This is the motivated industry to use our neurosymbolic solutions. I try very hard to sell these things to Great Bay Area. In China, they're called Great Bay Area to compete with United States. Bay Area, Great Bay Area is actually Hong Kong, Shenzhen, and Macau. I found that the problem, no matter polling AI, NASDAQ just listed as well last November, they want maturity level 6, 7, 8 above. Our neurosymbolic is open source, archive. It's far away from what they want. So I really want to spend time in Europe, maybe Pyro together, to develop something more mature to facing industrial for them to use. We have the CAV co-located with CAV this year. That's the reason I'm bypassing here and go to Croatia to present this third TSE’24. We have a Shona meeting and DAX meeting to pushing forward using large language model and neurosymbolic. And thanks for my collaborators and thanks for my students. That's all. Thank you. Thank you very much.